Hello everyone and welcome back. Before we start, open new file next to this video. It's the ML Core Foundation file and you can find it in your starter repository. So you can check it out on your GitHub and we can start right away. And that file is the spine of the whole track. And today we walk through three parts of it. We have section 6, it is a model strategy. Section 7 is a training. And the last one is evaluation. So keep it open and follow along with me. Let me just share my screen. Okay. Every concept today will be around these sections I just mentioned. So today is not just about talking about these models. It's about picking the right model for our question and then comparing it with the rule you already built, and then deciding if the evidence is good enough to change a real review queue. A model gives you a score, but we will still pick the target. We still design the test, and we still decide what we are allowed to claim. Okay, today has 4 jobs. First, we pick a method by starting from the question. Then we train a readable model before we try a flexible one. After that, we judge a review queue with a metric that matches the work. And lastly, we attack the results with harder tests. These 4 jobs are also the 4 promises I made you in week 2. I said I would explain what the random forest really does. I mentioned we would pick a decision metric, and also we would catch a model that looks great on an easy test. And also we mentioned different ways of splitting the data, as I remember. And so we will talk about all of these. Okay, one comparison contract. Okay, here is the contract for the whole lesson. The rule and the model must see the same rows. We should have same folds, same metric, same review depth, and the same policy when 2 scores are equal. We should put the base rate next to them and keep every fold. Also, we must read the wrong cases before we write the conclusion. And why so strict? Think about it. Say we test the rule on new clients, but we test the forest on random rows from clients it already knows. Both tables say precision on 50, but those numbers are not competing. And one of them took a much easier exam. It already knows the data. And we freeze the rule first. Because if you change your thresholds after you see the model or results, you are not comparing anymore. You are intentionally looking for the answer you wanted. And this contract is more important than which model you pick. And in previous weeks, we said something important. A lot of good product decisions should stay as rules. Rules can be faster, cheaper, and easier to keep alive. And when your data or your labors are weak, a rule is often the right choice. And we are not taking that back today. But this problem is different. We have a real decision. Which pages should reviewer open first? We have one row per page. We have features we can see before the decision, and we have a real outcome that happened after. So we have already enough pages, and we need to figure out the way to beat our current rule. After we look on all of this, it's fair to say we are ready for some ML experiment. And this doesn't mean the model is ready for production. And surely it will need calibration, monitoring, cost checks, and someone actually to own it. But today, we only ask one thing. Can we contribute more with our ML today? Start with the answer your decision needs. Do you need to see what moves together, or maybe group pages that looks alike, predict or maybe rank something? The questions you ask at this point will pick the method for you. And this is a good place to use your AI assistant and start prompting him. So be creative there and keep using our MD files that I mentioned in the beginning, since this is your full blueprint for your agents. And there you have almost every single question that could be asked in order to make a decision. You can chat directly with your dataset on a Hugging Face and ask the agent to clarify what questions should or could be asked with the data we have. And then you are the one who decides. The assistant should never quietly invent your decision, your target, or your boundary. So write one sentence about your code to understand why you are using such method and what your decision needs. And if that is not clear enough for you, you are not ready to pick a method yet. Okay, we have 9 methods and 9 different jobs. Okay, these are 9 methods in the toolkit, but these are not all methods, or I mean all models. They are not swappable. Some needs a target and some don't. Some give you a probability, some gives you groups, and some only help you look inside a result you already have. So use the number to keep your place, but pick by the job. And now I will walk you through these. And for each one, we will have what it is, when you use it, how it works, and how you check it. Okay, method number 1, transparent rule baseline. So a rule baseline is a policy that you write yourself, and nothing here is learned. Here is ours. If April clicks are below March clicks, we flag that page, and then we put the biggest page first. And pretty much that's it. You wrote the whole logic and the data did not. So when do you use it? Pretty much always and before any model, because it tells you what the model has to be. And it also puts your current assumption in plain words, where everyone can argue with it. Then you run it on the same rows, the same folds, and the same metrics, and the same K as every model. And you phrase it before you look at any learned result. A weak rule is still fine if it is fair and you can trace it, but a silly rule proves nothing. And don't stop at that rule either, because if the pattern is tangled and model really helps the decision, then you should use the model. Method number 2, signal analysis. Signal analysis asks a very simple question. What moves together with the thing I care about? So here is an example. We split the pages into buckets by how many active days they had. And then we look at the decline rate inside each bucket. And you can also use correlations, medians, small tables, or small plots. What you get from this is a measured relationship and not a prediction for each row. So you use it when you are exploring, or when you are checking an assumption, or when your target is still too weak to predict. Then show the direction and show the size. And always print how many rows are in each bucket. After that, check if it still holds for another client or another month. And a flat result is valuable too, because it stops a story that nobody can support. But here is the limit, and it really matters. This does not tell you that changing the feature will change the outcome. It only tells you where to look next. Method number 3, k-means clustering. K-means puts rows into groups when they sit close together. And there is no target here, so nothing to predict. Here is an example. We group our pages by reach, click-through rate, position, and activity. And then we look at what came out. Maybe one group is big, steady pages. Maybe another one is small, new pages. And maybe one group means nothing at all. So you use it when your question is which pages look alike. First, you scale your features, then you pick a number of groups, and the algorithm moves the centers around until things settle. And then you go and look. And that last part is really the work. Try a few values of K. Try different seeds and try maybe another month. Look at the group sizes and look at real pages inside each group. And then ask if different group would lead to different actions. Because k-means gives you group numbers, but it does not give you names or meaning. You do that part. and actually you can do it with your AI, right? And if changing k relabels everything, maybe it does. Or if every group leads to the same action, then it is not useful yet. Method number 4, logistic regression. Logistic regression works on a yes or no question. It takes your features, it gives each one a weight. It adds them all up, and then it bends the total into probability between 0 and 1. So a page might come out at 0.72, but careful, that doesn't mean clicks will fall by 72%. It only means the model thinks the page is likely to be in the decline group. So you use it as your first learned model because it is readable, and you can print the weights and see what it leans on. First, you scale your numbers, and then you fit on the training rows. And then you score the hell out rows through one pipeline. And after that, you check it with the base rate, precision at K, group folds, and the wrong cases. And remember what those weights really are. They tell you what happened inside this model, but they do not prove a cause or and when the real pattern is curved. Or maybe when two signals only matter together, a straight line will struggle in that scenario. So that is exactly the moment when a tree earns its turn. Method number 5, decision tree. Decision tree learns chain of yes or no questions. So one branch asks if active days are below some number, and the next one asks if impressions are above another. And at the end of every path, there is a leaf, and every row in that leaf gets the same score. So if you keep it shallow, you can print it and read the whole thing out loud. You use it when you want to see the logic. So limit that, ask for enough rows in each leaf, and fit it only on training data. But watch two things here. First, a tree will happily chase a small quirk that means nothing. And second, a shallow tree gives you only a few different scores. So a lot of rows end up with exactly the same number, and that really matters when you cut a top 50. So being readable does not save you from needing a type policy and hard test. Method number 6, it's a random forest. Okay, here is the one I promised you in week 2. Random forest grows a lot of decision trees, and then they vote. And each tree sees a different slice of the rows and a different sets of columns. So one tree might lean on reach and activity, and another one on momentum and position, and so on. Now, one tree on its own memorizes, but when many trees each memorize something different, most of these mistakes cancel out. And what is left is the part they agreed on. And that is why a forest can catch things that a straight line or one small tree will miss. So you use it after you already have your rule and a readable model. You fit every tree inside the training fold, and then you score the hell out fold, and you should know it's limited to. More trees will not fix a weak target or an easily split. And if a familiar client sits on both sides, then a forest is a very good at recognizing the client instead of learning the pattern. Method number 7 is gradient boosting. Gradient boosting builds small trees one after another. And each new tree only works on what is still wrong. So think of it like this. You start near the base rate, and then you add a small correction. Then you look at what you still got wrong. And then you add another correction. And the final score is all these little fixes added up. You use it when you need strong performance on table data. And when you already have the simpler models and when you have time to tune it properly. So you tune inside the training data. And then you compare on outer folds that you never touched. And please don't add boosting just to make the notebook look advanced. Because if you keep picking settings by checking the held out fold, then that fold is now part of your model, and it is not the test anymore. So when a simple method does about the same, take the simpler one, and you will be able to explain it as well. Method number 8, PCA. PCA takes a lot of columns that overlaps and it squeezes them into fewer new ones. And so here is ours. Impressions, clicks, sessions, and active days all move together. And PCA can turn these four into one direction that roughly means reach and activity. It finds that direction from the numbers alone. So it does not know it does not know your target, and it does not know your name, anything for you. That part is your job. So you use it to see many related fields at once, or to compress them, or to help with clustering. First your scale, then you fit it in training data if it fits inside a model. And then you look at what went into each component and how much spread it kept. But don't show a pretty two-dimensional picture and call it a proof that real groups exist. And if your columns are already few and readable, then PCA can take away understanding without giving anything back. So we need to be really careful with this method. Method number 9 is permutation importance. Permutation importance asks one question. If I take this column and shuffle it into nonsense, how much worse does my model get? So we shuffle active days across the held out rows and the score drops. Then we shuffle another column and almost nothing happens. And that tells you this model was leaning on active days. You use it after you already have a model and a score. So you measure, then you shuffle one column, then you measure again. And then you repeat it across the folds. And you should look at the spread and not just at the order. Our folds disagree a lot there. So I'm not going to give you a ranking that I cannot back up. Also, when two columns carry the same information, shuffling one of them hides nothing because the another one still tells the model what it needs. So this is a tool for looking inside a model, and it is not the model itself, and it says nothing about cases. Okay, choose the smallest method that answers the question. Now let's squeeze all 9 of them into one decision. So no target. Then use signal analysis to look at the relationships, or k-means to find candidate groups, and PCA only if viewer access actually help. But do you have a future, yes or no? And then you start with your rule. And after that, logistic regression or shallow tree, and you try a forest when signals might work together. Treat boosting as optional and use permutation importance only after you already have a fitted model. And this maps straight into the capstone questions too. Descriptive signal work does not need a classifier at all. And archetype work needs clustering and not accuracy. Decline and engagement questions can use supervised model if your label and your split holds up. And sparse AI referral data should start with exploration and not with classifier. So complexity has to earn its place by improving the real decision under the same test. Training just means Training just means the model learns its settings from examples, and overfitting means it learns something that works here but falls apart out there. So let me show you what happens on our own pages, because ours has a very specific shape. So look at our clients. One of them all on its own. It's quarter of every row we have, and they do not behave the same. In one of our tests, only a third of the client's pages fell, and in another one, almost two-thirds fell. Same month, same rules, but very, very different clients. And now here is the problem. Their pages also look different with different traffic sizes and different positions. So the model can work out which client a page came from without anyone telling it. And once it can do that, it does not need to learn what a failing page looks like at all. It can just think this smells like that client, and that client drops about a third of the time. So let's say a third, and that's memorizing. And it is not learning anything about the client. It is learning names. And a lazy split will pay it for that. Because if the same client sits in the training rows and in the test rows, then the model gets marked on pages from a client it already knows. So 3 marks. So how do we stop it? With one line. We keep every line on one side only. And then the pages it is judged on come from a client it has never met. And a good score has to come from the pattern instead of from the name. And I want to be clear about that goal here, because this is the promise from week 2. We are not trying to build a model with no memory. So memorizing is normal, and it is fine. What we want is that it still works on pages it has never seen. And we will find out later today whether ours does. All our example stands on the 1st of May 2026. So February, March, and April give us the features, and May give us what actually happened. And June stays sealed. We never open it. A page gets the decline label when my clicks fall below 80% of pay-per-clicks. And to be eligible, a page needs at least 1,000 impressions across the window and at least 10 clicks in April. So that leaves us more than 60,000 pages from 36 clients, and about 42% of them decline. Now, that label is a proxy. It is not a business outcome, and it is not proof that refreshing the pages would have helped. And those eligibility numbers are part of the deal, because if you change the thresholds after you see your results, then that is a new experiment, and you have to rebuild the rule and the model together. Okay, 9 features and deliberate exclusions. The model gets 9 fields, and every one of them exists before May. And so we have total impressions and clicks over the window, April impressions and clicks, February clicks, momentum from April against February, CTR rate, weighted position, and active days. And weighted position really matters here. We take total position divided by total impressions and not an average of daily averages, because that quietly gives a tiny day the same weight as a huge one. Now, what we left out, client and contents IDs are grouping keys and never features. Make clicks and impressions build the label so they cannot go in. And we drop the session, scroll, and AR referrals fields, because they are only there some of the time. We have a very, very huge gap there with this data. And a 0 before tracking started does not mean that nothing happened. And one more number to hold on it, or to hold on to. The biggest client is about a quarter of all of our rows. and the top 5 are most of the frame. So that is why the split is about to matter so much. Okay, about the method 1. Now let's run the rule on the real 16K pages. And remember, it was written before we looked at any model, and nothing in it was fitted to the main answer. So the rule flags 6,503 pages. And here is what happened to them. About 38% kept falling in a May, and the other 62% did not. So a page that dropped for 1 month mostly does not keep dropping, it bounces back. Now, stop and look at that for a second. My rule assumed the fall keeps going, and the data says the opposite is more common. That does not tell us why, and it does not make the rule stupid, but it shows you the assumption I build in out in the open where you can argue with it, and that is exactly what baseline is for, because you can see what the model has to improve. Precision at K asks one thing. Of the first K pages that we sent to a reviewer, how many really fell? So say 6 of the first 10 did, then precision at 10 is 0.6. And K is your review budget. It's not your model setting. It is how many pages a person can actually open. So always put the base rate next to it. And then you know what guessing looks like. Our main number is precision at 50 because that is the size of the queue. And we also look at the 10 and at 100 to see if the signal changes as the list gets longer. ROC, AUC still helps for the whole ordering, but it can hide what is happening right at the top. And this is the second promise from the week 2. So we pick the metric from the decision and not from the habit. Metric types, different kinds of output need different checks. So yes or no answers needs precisions, recalls, and F1. Ranked queue needs precision at K because only the top matters. A forecast needs error over future periods. Cluster needs stability and whether a human can actually use them. And a decision system eventually needs cost and value. So don't borrow a metric from the next door just because the library prints it easily. Accuracy can look lovely when one class is common, and it still tells you nothing about your top 50. Silhouettes does not turn groups into useful archetypes, and a number between 0 and 1 is not calibrated probability just because it sits there. So name your output always first, and then pick the metric that tests how that output gets used. Okay, section 8 is about the evaluation and validation. Section 8 asks how we know a model works. What baseline does it beat? Which split matches how it will really be used? Which metrics reflect the real decision? Maybe are the results stable? And do we understand what we still don't know? And we can answer 4 of these right now. Our baseline is the frozen click rule, and our metric is precision of 50. Our deployment question is a new client, so we group by client. And because the portfolio is so lopsided, we keep all 5 faults visible instead of hiding behind an average. But 4 of them are still open. We have not tested calibration. We have not tested causal impact. We have not tested production value. And we have not done full walked forward validation. And this is how a framework is supposed to work. It is not a checklist that you tick. It shows you what your evidence covers and what your conclusion still has to admit. Okay, split types. A split is just a line between what model learns from and what we tested on. But which line you draw is really a question about the future. So random rows ask, what about a new row from clients we already know? Grouping by clients asks, what about the client we have never seen? A time split asks, does last month still work next month? Geographic asks about new places, and user splits stop one person from landing on both sides. For us, grouping by client is the main test because a lot of our pages share a client. And the real question is whether this works for a client we have not met yet. Our main label does give us a future window, but that alone is not full-time validation. And if you will cross both boundaries in real life, then a combined client and time design is stronger when your data can carry it, of course. Split is a deployment question. A random split and a grouped split do not just cut the percentages differently. They ask completely different questions. So random rows put pages from the same client on both sides. Which pages the model sees that client while it trains, and then it gets tested on more of that same client. But grouping keeps every client on one side only. So the client in the test are strangers, and neither one is right in general. Random is fine when the rows are truly independent and when you will stay inside the same mixture. Grouping is right when you have to work for a new client, and time is right when you have to work next month. So first you write down the case you are deploying into, and then you pick the split, and then you add an assertion in code what the overlap is zero. That the overlap is zero. Your AI assistant is quite good at writing that check and at writing to even break it. But you are the one who decides which boundary matters. Okay, look at this. On the random split, the forest gets the top 10 right, every single one and in every fold. And at precision at 50 is basically perfect too. Now, that should make you suspicious and not happy because nothing about the model changed and nothing about the features changed. The only things that changed is where we draw the line. And the easier boundary let the same client sit on both sides. So this number answers a much easier question than the one we actually care about. And this is the third week 2 promise paid right there. We coded and not with the training curve. We coded with by changing the exam to match how it really gets used. And then watching the number move. So ask your agent to attack your split, which things repeat, maybe which periods overlap, what got fitted on everything at once. And then you check every answer yourself and in your code. Now, we keep every client on one side only. The same forest, the same rows, the same features. And the top 10 goes from 10 out of 10 down to about 4. But don't call that the fake number because it answered its own question fairly. The mistake would be to use it to talk about new clients. And the second thing here matters just as much. The result swing a lot depending on which clients we held out. So when what we can actually say is this: the forest has some real ranking signal, but the portfolio is uneven and the estimate is shaky. So that plan sentence is worth much more than reading your 4 decimals, and the exact numbers live in the receipt if somebody wants to audit that part. Now, let's put everyone on the same test with the same folds, the same rows, and the same metric. So the rule gets about 39%. Logistic regression about 42, the shallow tree about 43, and the forest about 50. So the forest has the best average, and it is about 10 points better than the rule on the top 50. And that is the headline, but it's not the conclusion yet. Look at the dots here, because each one is a fold, and they spread out of long way. Those averages are made of 5 different sets of held out clients. The received has the AUC and the other K values too. But I want one metric tied to one real review workload here. And when we look at the folds one by one, before we decided this improvement is actually real. So here is the forest minus the rule inside each fold. In 3 folds, the forest is better, and in 2 folds, it is worse. And so what can I actually say there? The average points the right way, but there is no stable winner across 5 sets of unseen clients. And logistic regression is up and down against the rule too. And this is exactly why we kept the row folds, because an average can hide the times when it flipped. The folds also start from different outcomes rates. So some queues are just easier than others. Testing everyone on the same fold shares that difficulty, but it doesn't mean it removes it. So I'm not going to announce that forest win. It's so hard to decide, and we need so many more data and tests to do. And I'm not going to throw the signal away either. So we report only the direction and the wobble together. Okay, exact ties can choose the queue. A shallow tree gives every row in the same leaf the same score. And in one of our folds, thousands of rows set on exactly the same number, right where the top 50 gets cut. So think about what that means. If you take 50, then something else is deciding who gets in. Maybe it is the order the files was written, or maybe it is alphabetical, and now that thing is part of your model, and you never even wrote it down. Ours sorts by score, and it only breaks exact ties with the seeded hash. And the received records how many rows share every cutoff. And in a real system, you might break ties by reach instead. And that is fine. But then the rule plus the tie break is the system. And you have to test both together. The forest has distinct scores here, so this is not driving our main result. But every top K number should say what happens when scores are equal. A global queue and a per client queue look very, very similar, but they are not the same job. So one central team might work the 50 biggest opportunities across everything, and that is 50 pages. Or you give every client their own top 10. And in our frame, that is 273 pages. Same idea, but 5 times the work. So the precision numbers are not competitors, and there is a second choice hiding in there too. Macro precisions gives every client equal weight, and pooled gives every page equal weight. So you pick from what you promised. If every client must get attention, then coverage matters. And if one team chases the biggest win, then the global list fits better. So always say who works the list, how big it is, and how you averaged it. Because a metric without its workload makes 2 very different systems look the same. A metric tells you how often, but the wrong rows tell you why. So here is one we got wrong in the confident direction. It has a high declining score, and its clicks actually went up in May. And here is one we missed completely. No clicks in February or March, then a big jump in April, then down in May. our momentum feature goes a bit wild on a page with almost no history. So the next test is not same grand story. It is a flag for pages without enough history or a window per client. And that is a real small testable next step. And this is another good spot for your assistant. Give it the error rows with the identifiers stripped, with the identifiers that are stripped, and ask it to group the failure patterns and to say what evidence would kill each idea. But don't ask it to invent a cause from these two rows. And keep the rows private and publish only what the claim really needs. Sensitivity shows what the results depends on. Several of our features are click counts, and April clicks also help to define the label. So let's check whether that is doing the work. So we run the whole group test again with every click level feature removed, and the result gets weaker. Now, that does not make those fields illegal because they exist before the decision point, so they are fair. But it does tell you that the headline leans partly on fields that are close cousins of the label. And permutation importance points at active days on average. But it swings so much between folds that I will not give you a ranking. So here is what I can actually say. What the model leans on is not stable across clients, and its leads shrinks under the stricter feature set. And that turns the model work in a much better much better question. What has to stay true for this to hold? And we are back on our notebook, and I want to say a few words about this. And as we already know, your notebook has 5 steps. First, you name the method and say why it fits, and then you define the target, the decision point, the population, and the split. After that, you train and compare against your week 4 baseline under the same contract. Then you look at your errors, your ties, and your edge cases. And lastly, you run the self-check and execute it from top to bottom. And use your assistance where it saves you mechanical work. So inventorying the schema, drafting a pipeline once your contract is fixed, writing the split and leakage assertions, summarizing faults, and critiquing or critique of your work. But stop it when it wants to change your data set, your target, your split, your population, or your metric, because those are experiment design and they are yours. So you need to read me MD file, then load training evidence, first models, and FlyRank data. Write down your seeds, keep row levels exports private, and finish with one table that someone else could reproduce. Okay, some quick practical answers. You submit your repo URL just like we explained many times. We always just submit our same GitHub repository URL. Okay, and if you change them, you can just provide another link. It's fine. The warehouse is there if you want it, but you don't need it all the time, maybe. So your final evidence should show the baseline, the model, the base rate, the split, the metric, K, the faults, and your tie policy. And a short note on the errors. The card has the checklist, and this video adds nothing extra to it. So you can use AI, your agent, and everything to simplify some work, to explain you some concepts and things that are not clear enough to you. And pretty much that's it. And we are going back to the research paper I mentioned in the previous weeks. So this week you also get our research paper in the starter repo. So read it before week 6 with 3 questions next to you. Which pages and which time window produced each headline number, and many others. So we need to do stuff one by one, and we will do this session in some interactive way, and I will try to provide as much value as possible for you guys, so you can use this part and place it inside of your portfolio, inside of your CV, and you reuse it, repurpose it. Uh, so it will depend on what your goal is. If your goal is to enhance your current portfolio, or maybe to have some social media exposure to create some posts. So pretty much very cool stuff could be done there. And yeah. Okay, let's close this whole loop. So you open your core framework, you pick the method from the question, and you freeze your baseline. You keep the rows, the folds, the metric K, and the type policy the same. Then you test the boundary you actually care about, and you read the folds, the ties, and the wrong cases before you name any winner. And then you commit the notebook, submit your repo, and submit your assignment, and pretty much that's it. Strong week 5 is not the biggest score, and is not the longest list of models you tried. It is the smallest claim that your evidence can carry attached to a decision that somebody can actually use. So open your notebook, play with it, do your work, submit your assignment, and I see you in the next week. Take care.